Okay, in order to find the inverse of this log function, my first step is to rewrite g of x to be y. So I have y equals log base 3 of x plus 7 minus 2. My second step is to then switch x and y. So now I have x is equal to log base 3 of y plus 7 minus 2. My next step is to then isolate and solve for y. In this case scenario, I will add 2 on both sides. This will leave me with x plus 2 is equal to log base 3 of y plus 7. My next step is to then convert this to the to the exponential form. So this will turn into 3 to the power of x plus 2 is equal to y plus 7. My next step is to then subtract 7 on both sides. Keep in mind that the 7 and the 3 are not like terms, so keep them separated. And this will leave you with 3 to the power of x plus 2 minus 7 is equal to y. So did I get y all by itself? Yes, I did. So my final step is to rewrite this to be the inverse of g of x. So I have the inverse of g of x is equal to 3 to the power of x plus 2 minus 7. Let's go ahead and box that in. Moving on to our next question, we need to find the inverse of the following exponential function. In this case, my first step is to rewrite f of x to be y. So I have y equals 5 to the power of x plus 3 minus 2. My next step is to then switch x and y. So now I have x is equal to 5 to the power of y plus 3 minus 2. My next step is to then isolate and solve for the new y. So I will add 2 on both sides. This will leave me with x plus 2 is equal to 5 to the power of y plus 3. My next step is to then convert this to the log form. Keep in mind that the inverse of the exponential function is the log function, and the inverse of the log function is the exponential function. So I have log base 5 of x plus 2 is equal to y plus 3. My next step is to then subtract 3 on both sides. Keep in mind that the 3 and the 2 are not like terms. Keep them separated. So this will leave you with log base 5 of x plus 2 minus 3 is equal to y. From there, I will then convert this to the inverse notation. So I have the inverse of f of x is equal to log base 5 of x plus 2 minus 3. Let's go ahead and box this in. Moving on to the next question, we have to solve for the following log. Keep in mind that if there's no base written down, it is always known to be a base of 10. Or, better yet, it is known as a common logarithm. From here, I will go ahead and convert this to the exponential form. Keep in mind that I can only do this if the log expression is all by itself. So I now have 10 to the power of 2 is equal to x squared plus 19. I know that 10 squared is 100, so I have 100 equals x squared plus 19. I will then subtract 100 on both sides. Keep in mind that the reason why I'm doing this is because I want to move all the terms to the side that contains the positive x squared. So I do minus 100 minus 100. This will leave me with 0 on the left, and I end up with x squared minus 81 on the right-hand side. Notice that I have a difference of squares, correct? So I do what? I take the square root of the constant. I have 81, so this will give me plus or minus 9, as the following factors for the difference of squares. So now I have what? X plus 9 times x minus 9. I will then set these two factors to be equal to 0. So I have x plus 9 equals 0, and I have x minus 9 is equal to 0. For the first solution, we will end up with x is equal to negative 9 because I move 9 to the other side. And for the second solution, I end up with x equals positive 9 because I add 9 on both sides. Okay, moving on to the next example, we have to solve for the following log equation. My first step is to isolate for the logarithm. Looking at this logarithm, I notice that the expression is all by itself, so I can convert this to the exponential form. So I have 5 to the second power is equal to 3x minus 2. We can rewrite 5 squared to be 25 is equal to 3x minus 2. I will then add 2 on both sides to isolate for x. This will leave me with positive 27 is equal to 3x. I will then divide both sides by 3, and this will leave me with a final solution of x is equal to 9. Moving on to the next question, we have to go from a description to a function. So it says, write the function for a log function with a base of 4 reflected over the x-axis, vertically compressed by a factor of 1/4, and shifted to the right 1 unit and down 3 units. So for this one, I have y is equal to, we have a reflection, so that's going to be a negative, and it's going to be vertically compressed by a factor of 1/4. So we have negative 1/4 in the front, times the log base 4 of, we have a shift to the right, so it's going to be x minus 1, close parentheses, and then down by 3. So this will be minus 3. And that's going to be our final solution. Let's go ahead and box it in. Moving on to the next question, we have the following description. Write the function for a log function with a base of 4 shifted right 10 units and up 3 units. So for this one, we have y is equal to log base 4 of, we shift to the right, so it's going to be x minus 10, and then it's going to be up by 3, so plus 3. And that's going to be our final solution. Let's go ahead and box that in. Moving on to the next question, we have to identify the following: the domain, range, as well as the vertical asymptote for the following function. We have log base 3 of x plus 2 minus 2. My first step is to identify the domain. Keep in mind that the domain is identified by just simply looking at the terms within the parentheses. In this case scenario, I have x plus 1, set it to be greater than 0. We then isolate for x by subtracting 1 on both sides. This will give us x is greater than negative 1. And from there, we're going to write down all 3 notations. We have the inequality notation that we just wrote down, that x is going to be greater than negative 1 for the domain. We also have the interval notation from negative 1 to positive infinity. And we have the set notation, which is going to be all x's, or for all x's in which x is going to be greater than negative 1. Now, for the range, keep in mind that for the range, we have mentioned before that the range will be for all real numbers. So we have it for the interval notation from negative infinity to positive infinity. We have the set notation, which is given to us by, for all y's, in which y is going to be an element of the real number set. We also have the verbal description, all real numbers. Okay, now for the vertical asymptote, it is identified by just simply looking at the terms within the parentheses, exactly what we did for the domain, but instead of setting it to be greater than 0, we're going to set x plus 1 to be equal to 0. So from there, we isolate for x by subtracting 1 on both sides. This will leave us with x is equal to -1 as the vertical asymptote. Keep in mind that this is a line that we cannot cross. We get very close to it, but we cannot cross it. And visually, it is graphed using a dashed line. So let's go ahead and graph it. Keep in mind that for these little squares, it's all going by ones. So we're going to graph x equals -1 first. So that line is going to be right here. X equals -1. Okay. And from there, we're going to identify at least one, possibly 2 points of accuracy for this function. So let's go ahead and do that. If we go to Desmos, we have y equals log. Let's see all the way down here. We have log base 3 of x minus 1. Oh, no, that's a plus 1. And minus 2, plus 1. So plus 1, minus 2. There we go. So now we click on the gear button. If we click on the gear button, we have the following points of accuracy. We have one at 0, -2. And we have another point of accuracy at 2, -1. And that seems to be it for now. We do potentially have that other point of accuracy at 8, 0. If we can fit that in, definitely we can definitely plot that in. So let's see that again, 0, -2. So this is 0, -2 right here. We also have 2, -1 right here. We have 8, 0. Whoops, that's not 8, 0 right there. That's 8, 0. And let me just verify that again. Okay. All right. So now when we connect these points, the graph is going to look something like this. It doesn't have to look perfect. It's just a rough sketch. Okay. It's just a rough sketch. We're going to put the arrows to indicate that the graph is continuous in both directions. Okay. Now, let's move on to the next part. It says a school district in Texas recently purchased a set of high-end graphing calculators for $14,500. Because of rapid advancements in technology and daily wear and tear, the value of this equipment is expected to decrease at a steady rate of 12.5% per year. Okay? Now, it doesn't say it here, but it should say that this is in 2014. Okay, write that down, 2014. If I didn't write it down on your paper, hopefully it should be there or we do it together in class. Okay, so from there, what do? Well, we know that we are given the initial value. $14,500 is going to be the initial value A. We also have the R value given to us by 12.5%. So we then convert that to the decimal portion, or the decimal format, which will be what? We have 0.125. Okay? Now, keep in mind that this is a decreasing function, right? It says decrease right there, so this will be a decay, an exponential decay function, which means that we have to identify what the 1 minus r will be. In this case, if I do 1 minus the 0.125, then we're going to get 0.815. Okay, now based on this information, we're going to set up our function. We now have v of t is equal to the initial value, 14,500, times the rate of change, which is now 0.815 to the power of t. Okay, now from there, we're going to, or excuse me, that should have not been 81.5. Let me fix that real quick and fix that right there. Let's see, that should have been 88, so that's going to be 87.5. My apologies if you caught that in class. Good job. Okay, so now we do what? We type this function in for the part B. It says using your equation, what is the estimated value of the equipment after 6 years, round to the nearest whole number. Okay, all right, so let's go ahead and take that information. We have, let's see, on Desmos, we have 14,500, parentheses, 0.875, close parentheses to the power of 6. Okay. And look at that. We ended up with $6,507.53. But if we round to the nearest whole number, this will be what? $6,508, correct? All right. So let's go ahead and put this onto our document. It's $6,508. Okay. So we have, let's write it down. V of 6 is going to be 14,500 times 0.875 to the power of 6. We're just showing our work. And V of 6 gave us $6,508. Okay, and that was the final solution. Now it's asking us, using your equation, estimate after how many years the value of the calculators will first drop below $5,000. Now, hopefully I fixed this on your document by the time that you watch this video, but this will specifically say at what year will the calculators first drop below $5,000? At what year? Okay. All right. So what do? This means that we're going to look at our calculators and we're going to type in the following. Y equals $5,000. We're going to type in the original function, 14,500 times 0.875 to the power of t on the calculator. And what we're looking for is the point of intersection between these two lines. So let's go back. We're going to go back here. We're going to replace that with a t. There we go. And then we have our y equals 5,000. And this is going to be a very large number, so you do have to quite zoom out right here. Let's see if we zoom out. Yep, there we go. All right, so now when we click on the point of intersection, we're going to get 7.97, or essentially 8 years, okay, if we round to the nearest whole numbers. So this is going to give us a time frame of 8 years. So we're going to add this to the original date in which the calculators were purchased in 2014, okay? So if that's the case, that they were purchased in 2014, we do what? 2014 plus 8 years, and that's going to go ahead and give us what? 2022. So the price of the calculators will first drop below $5,000 in the year 2022, after 8 years.